In the last class, we discussed about compound pendulum. We will continue the discussion. So we know that the compound pendulum, suppose this is the compound pendulum with some random shape, and this is the point of suspension. This is the point of suspension, and suppose this was the center of gravity, and this was the center of oscillation. And the distance between center of suspension and center of gravity was L, and the distance between center of gravity and center of oscillation was taken as L dash. Now the time period of the compound pendulum was obtained in the last class as T equals 2 pi root over K square plus L square upon GL. So also we obtained the time period of an equivalent simple pendulum, that is a simple pendulum having the same period as this compound pendulum but with a different length. So the equivalent simple pendulum time period was given by 2 pi root over L by G, where L was K square plus L square upon GL, which was also equal to L plus L dash. All these things we have discussed in the last class. So this can be, not G, K square plus L square upon small l. So this can be further written as K square upon L plus L equals L plus L dash, and K square L cancels and K square equals L dash. So this value is a constant. And now this can be written in terms of L and L dashes. T equals 2 pi root over L plus L dash upon G. So this is the time period of our compound pendulum. So these are different expressions of the time period of the compound pendulum. Now what happens if we invert the compound pendulum? That is, we suspend the compound pendulum in this point. That is, if we invert the compound pendulum, the center of oscillation comes here, center of suspension comes here. So this is center of suspension and this is center of oscillation, and this is center of gravity. This distance was L and this distance was L dash. So again, the time period of this inverted compound pendulum will be T equals 2 pi root over K square plus L square upon GL. Instead of L, the new length will be L dash because we have inverted the pendulum. So this will be K square plus L dash square upon GL dash. Now in place of K square, we can substitute the value L dash, which will be 2 pi root over L dash plus L dash square upon G L dash. So we can take L dash common here and the L dash in the denominator cancels. So the remaining value will be 2 pi root over L plus L dash upon G, which is same as the time period of the original compound pendulum. Both are the same. So what we have obtained is that it is possible to interchange the center of suspension and center of oscillation and still the time period will be same. Now we have 2 points about which if we oscillate the compound pendulum we will obtain the same period, and it is also possible to find other points in the same compound pendulum in which we will obtain the same time period. We can do that by taking this term taking this term or this value of time period, which is t equals 2 pi root over k square plus l square upon gl. We square this squaring. T square equals 4 pi square k square plus l square upon gl. And now simplifying, we'll get t square g upon 4 pi square times l equals k square plus l square, or l square minus g square gt square upon 4 pi square times L plus k square equals 0. So this is a quadratic equation in L, and we know that for a quadratic equation of the form ax square plus bx plus c equals 0, if roots are x1 and x2, then sum of the roots is given by minus b by a, and product of the roots is given by c by a. Similarly, if the roots here are L1 and L2, the sum of the roots will be minus b by a. Here b is the coefficient of x, or the coefficient of L here, which is minus gt square upon 4 pi square. So minus this minus, the b will be minus gt square upon 4 pi square upon a. A is the coefficient of L square, which is 1 here. So this will be gt square upon 4 pi square. And the product L1 L2 will be c by a. C is k square here, k square upon 1, which is k square. So we have obtained that the sum and product are both positive, which means the roots L1 and L2 should be positive individually. That is the only case possible. You can just verify that. And now, if this is our compound pendulum and this was our center of suspension and this was our center of gravity and this was our center of oscillation, and this length was L and this length was L dash. Now we have two more points, L1 and L2. L2 which have the same time period as these points. So if L1 equals L, suppose we take L1 equals L, and we know that the product L1 L2 equals K square. We know that L1 times L2 equals K square. So if we take L1 equals L, then L1 equals L, then L2 should be K square upon L. Substituting the value of L1 equals L here, then L2 should be K square upon L. L2 should be K square upon L. And we already know from here that K square upon L is nothing but L dash. So this will be L dash. So L1, if L1 is L, L2 should be L dash. So L1 measured from center of gravity, if we take L1 as L somewhere here, let's call this point as S dash. Then if this distance is L, then L2 should be somewhere here. L2 should be somewhere here, which will be O dash, and this distance will be L dash again. So these are the 4 points. I mean, if we oscillate the pendulum in any of these 4 points, we will get the same time period. So next we calculate the maximum and minimum time periods of a compound pendulum. Again, we know the time period of compound pendulum as t equals 2 pi root over L square plus K square upon GL. And squaring this, we will get t square equals 4 pi square times L square plus K square upon GL. Now we have this value, and to calculate the maximum and minimum time periods, we know that for maxima or minima, the derivative dt by dl should be 0, and for maxima, d square t upon dl square should be less than 0 or negative. For minima, d square t upon dl square greater than 0 or positive. So now we take the derivative of this expression. So this will be 2t dt by dl equals so I'm not doing the complete steps of derivation. You can do that by yourself. So final expression will be 4 pi square upon g times 1 minus k square upon L square. So for maxima or minima, if we substitute dt by dl equals 0, this value will vanish. So this term will also vanish. So finally 1 minus k square by L square will be 0, or k square equals L square. That means L equals plus minus k. But we do not require minus term because it doesn't have any meaning. So L equal to k is our value. But we don't know whether this is maximum or minimum time period, because we just know that this can be the length for either maximum time period or minimum time period. So now to find that, we just take the second derivative of this expression, and we will obtain the second derivative as 2t d square t upon dl square equals 4 pi square upon g times 2k square upon L cube. So this after we take the second derivative, we will obtain this expression, and substituting the value of L equals k here, so we will get the d square t by dl square equals positive. We will get the term as positive. A double derivative is positive, which means for this length, for length L equals k, time period is minima. So this is the length of the or the L value of the compound pendulum for which time period is minima. Now for maximum time period, looking at this expression again, for maximum time period, t should be maximum, right? For t to be maximum, if you substitute L equals 0 here, L equals 0 here means denominator is 0, which means t will be for L equals 0, t will move to infinity. This means L equals 0 means the pendulum is the point of suspension will be the center of gravity itself. So at that point, time period will be maxima.